Hello, Chemistry of Earth and Space Science. This is our fifth lesson in this unit. Today we're going to talk about covalent compounds and how molecular geometry plays a role. So objectives for this lesson, lesson 5, is to define what VSEPR is, valence shell electron pair repulsion, and how that plays a role here. To use VSEPR theory to predict the molecular geometry of molecules, given their formula, their number of substituents, how many lone pairs, essentially being able to draw a Lewis dot structure for a covalently bonded molecule, and then to use molecular geometry to predict the polarity of that molecule. So what's VSEPR? So VSEPR, as it says, stands for valence shell electron pair repulsion. That means that electron pairs, as well as bonds that contain electrons, in order to take up the least amount of stress on the molecule, are going to go as far away from each other as possible. So they will take a geometry, a three-dimensional structure that will have the electrons that are parts of bonds and the electrons that are not a part of bond, and try to spread them out as far as humanly possible. And what's going to happen is we're going to have very distinct shapes that have very distinctive bond angles. A bond angle is an angle between two different bonds on a molecule. So the shape of the molecule results when you're looking at how the electrons are arranged around the electron cloud. And when looking at this, every single atom in the compound brings its own electrons to the party. So we got that's going on, but only the valence electrons are going to participate in the bond and affect the shape. So even though there's a lot of core electrons in a lot of the atoms here, we're going to focus almost exclusively on the valence shell, hence the valence shell repulsion theory. So when looking at a molecule and trying to describe what that molecule might look like, first thing we have to do is identify what's going to be the central atom. That would be the atom that is at the center of the molecule's shape. So what normally happens is it is the one that's least electronegative, is not always, and it's also going to be the one that has the most bonds attached to it. And actually, when you have rather large compounds, every atom that is a central atom will have its own potentially unique geometry. The substituents, that's a fancy word for the atoms that are attached around the outside and can tell us what the central atom is going to look like around it. So I'm going to show you a few shapes, one for methane, one for ammonia, one for water, and one for carbon dioxide, just to give you an idea before we dive into what this process is about. So on the left-hand side is at the top, that's methane, that's carbon tetrahydride. What happens is when those substituents that are in two-dimensional space, as you see it on the screen, spread out into three-dimensional space, you see they take up this unique shape over here that is actually called a tetrahedron. You'll see that a lot through this presentation. Shape. But at the bottom, we have one pair of electrons here, the top ones, that are not a part of a bond, but are still part of making this molecule take a very unique shape. So notice this molecule over here, this is ammonia. It kind of looks like the bottom half of this tetrahedron. These atoms, because of these electrons here trying to spread out as much as possible, would not lay flat in a plane. Another couple compounds, one we've seen already, water. Water has two pairs, two non-bonding pairs. Those two non-bonding pairs keep this molecule from being linear. There's up on top here, and over here there's electrons that are pressing the other bonds away, making this appear to be what's called a bent shape. And sometimes, like the bottom one, which is carbon dioxide, it might take a linear shape. So if everything becomes very symmetrical and everything pushes nicely in even directions, sometimes you get this linear shape that is characteristic of carbon dioxide. So what I'm going to suggest you do is, before we move any further, before you go any further with these notes, go and do the first activity that's a part of your packet. It's a PhET for molecular geometry, and let me show you a little bit about what that's going to look like. So here's the PhET. If you just type in molecular shapes or PhET molecular shapes, you'll get this. If I play this, and let's do it with models, because what happens here is you don't take into account the weirdnesses that might be associated with different atoms making the pulls and pushes a little differently. Okay, so this is a molecule, sorry. And the purple one is the central atom. And I don't know what this is. It's just a matter of saying 3 atoms that exist. So if I put another bond onto this molecule, notice what happens to the other 2 gray molecules, 2 gray atoms. They move away. So now this is all in a plane, so you can see they're all in the same plane. Okay, so this is, if I had 3 bonds around a central atom, and they were all the same, and I had no other electrons here, this would be what the shape would look like. It's actually referred to as trigonal planar, in the shape of a triangle, but in a plane. If I added one more bond, notice what happens. Let's watch this. I'm going to do this like this. There we go. If I add one more bond, boom. Now, all 3 of those fell out of the plane. All 3 of those fell out of the plane and made this shape, and this shape is called the tetrahedral. So I want you, before you go any further with this PowerPoint and the notes, to play around with this and follow the instructions that are associated with the video or the PhET. So one thing I will point out is a couple pointers here to make things easier. Let's get rid of one of these bonds. Boom, go away. And suppose I wanted to add a lone pair, a pair of electrons that are not going to have an atom attached to it. Now, I can throw it on there and watch it bend everything around. See, it kind of bent this molecule, much like having a fourth bond is. These electrons on the top pushed it down. But if I want to see what that shape looks like, I can turn off the lone pairs. They'll still be there. They'll still be affecting the other bonds, but you just won't see them. So there you go. And if I wanted to show the bond angles, see what the angles are between this bond and this bond, I could click this one, and it'll say that's 109.5. So I would start by doing the PhET and then come back to the lecture. So hopefully you had some fun playing around with the PhET and all that it could do. I find myself just loading it up as much as I can and seeing what the shapes are. I will say, I'll bring this back up, I will say that we're going to deal with shapes that are only go up to 4 atoms. But honestly, it can go easily up to 6. And the shapes get kind of weird. So I played with that. If you come to Chem 2 and then finally to AP, in AP we focus on the larger atoms with the more bonds. But here in Chemistry, Earth, and Space Science, we're going to focus only on those that have up to 4. So there's a series of shapes that are pretty common, and one of the most common ones is linear. And linear is when they are, big surprise, they're in a line. That central atom that's in the middle can have 1 or 2 atoms attached to it. Of course, if there's only 1 atom attached to it, the, quote, central atom and the substituent would be in a line. But one way that one central atom with two substituents can form a shape would be making it linear, where everything gets balanced out, kind of like that carbon dioxide. Because of where those electrons are, you get a bond angle here of 180 degrees when that happens. We saw that in the very first example in the FET. Normally, this happens when you have double and triple bonds. They might not be always linear when you have a bunch of single bonds, because the octet rule, you'll see as you'll play around with it a little bit more, and I'll show you more examples, but linear is almost always with a double or triple bond involved. I can show you with a FET. So let's get rid of some of these bonds. And let's say I have just a double bond. Well, a double bond and a single bond, the only way that's going to form is with a linear formation. If I get rid of one of those bonds and put another double bond, that's going to be what happened with carbon dioxide. And here we have 4 bonds, which is what atoms want, because each bond consists of 2 electrons. The next common shape is just called bent. It's not the most fancy name for a shape, but it's just referred to as bent. That's when the central atom has 2 substituents, but also there's going to be non-bonding pairs. And depending on the non-bonding pairs, how many there are, you might have a angle that's 109.5, like we saw a little bit earlier, or you might go a little past 120. Let me show you that with the FET. So let's get rid of these, boink, boink, and add 2, right? And now let's add 1 lone pair. Doesn't give me a lone pair. Do I not have a lone pair? Oh, show me a lone pair. There we go. So when I add the lone pair, note that if I take them away, that angle between those 2 bonds becomes 120. If I add another lone pair, the angle between those 2 become 109.5. Now that's the by theory, everything's symmetrical configuration. Truth be known, these 2 sets of non-bonding pairs push a little bit stronger, and we'll squeeze this down a little bit closer to 107. Bent can be made with 1 non-bonding pair or 2 non-bonding pairs, but bent always happens when you have some non-bonding pairs involved. The next one is called trigonal planar. That's where you have those 3 atoms, 3 substituents connected to the central atom, and only those 3 substituents, no non-bonding pairs. Those angles are going to be 120. So going back to this, let's get rid of the lone pairs and just add 1 more. Let's do a double bond. You're still going to have the shape to be 120, each one of these angles. And they're all in the same plane, hence the fact they're called planar. So I can pull this down to show you. Okay. The next shape is trigonal pyramidal. Now, if you can imagine this shape on the right-hand side and pretend like that yellow one is a non-bonded pair, these 3 whites and the pink would make a pyramid that's shaped with a triangular base. This happens when we have 3 and sometimes 5 substituents. Normally it's 3 substituents and some non-bonding pairs to take this yellow non-bonding pair and push those other 3 out of the way. This is where the bond angle is around 107.5 when you have that 1 non-bonded pair. So it would look like this. I take my 3, add a non-bonded lone pair, and ta-da, if I don't show that, I get that trigonal pyramidal shape. The last one is tetrahedral. And this is a very, very common one because of the octet rule. Because the octet rule, each atom in the center wants to be surrounded by 8 electrons. Every pair of electrons is a bond. So you would have 4 substituents for those 4 bonds, and that would give an overall, what's called an electrical or electron geometry of a tetrahedral. Almost always, this shape comes when there's no non-bonding pairs and there's 4 substituents. Super, super common shape. So let's talk about how you would determine the shape of a particular molecule from the formula. So step one, you got to draw the Lewis dot structure. That's what we did in lesson number 4. You need to be able to draw the structure. You need to be able to determine the geometry of it. Know which one of your atoms is the central atom. Almost always it's going to be the one that's has the most bonds to it. Be pretty obvious. If it's not, in my mind, going to be obvious, I will go ahead and underline it to say, hey, this is the central atom. Then what you want to do next is count your electron domains. Now, this is where it gets kind of tricky. An electron domain is either a bond or a lone pair. A bond or a lone pair. So if I go back to my PhET, this shape right here has 4 electron domains. It has this bond, the bond in the back, and then this pair. 1, 2, 3, and 4 electron domains. If I were to get rid of this lone pair, I should get rid of a bond, and I were to add another lone pair, we still have 4 electron domains. 1, 2, 3, and 4. Every bond is an electron domain, even if that bond is a double bond. This still has 4 electron domains. 1, 2, 3, 4. Meaning a bond, no matter what size it is, single, double, or triple, counts as 1 electron domain. So you got to count how many there are. We may have 2, we may have 3, we may have 4. Come to AP chemistry, we might have 5, might have 6. But we're going to focus on whether we have 1, 2, or 3. And then from that, we'll determine what our electron geometry is. That means, assuming everything is the same, what is that geometry going to be? So if I go back to my neat little PhET, this thing has 4 electron domains. Its electron geometry is tetrahedral. Notice that if it's got 4 electron domains, it's going to be tetrahedral. Even if I take one of these non-bonding pairs and add a bond, I'm still going to get a tetrahedral shape. Okay? I may get a different overall shape, but I'm going to get a tetrahedral shape. If I have no bonded pairs and only bonds, I'm still going to get a tetrahedral shape. That's the electron geometry. If I have 3 electron domains, it's going to be trigonal planar. That's going to be like the core shape. And if I have 2 electron domains, the core shape is going to be linear. So that's what happens when we have, let's get rid of this double bond. If we're looking at non-bonding pairs, the lone pairs, as being part of the overall shape. Now that's going to be the electron geometry. There's 3 types: linear for 2, trigonal planar for 3, and tetrahedral for 4. So now, in order to determine the molecular geometry, we have to count how many electron domains there are, ED is electron domains, and how many of the electron domains are lone pairs. So if we have 2 electron domains, we don't have any choices. If we have only 2 electron domains, they're going to be a linear shape. That's the only option. So here I used, again, the carbon dioxide with 2 electron domains. No matter what you do, with 2 electron domains, it's going to be linear. There's nothing fancy there. However, if you have 3 electron domains, there's 2 options. One is like this, where we have no lone pairs. So if I go back to this and I say, let me get rid of my lone pair, and let me make, because I want to be the same as what I have there, I'll make that a double bond. This is what I had. This is my trigonal planar shape. I have a double bond, a single bond, single bond. That means I have 3 electron domains, 1, 2, 3, and none of them are lone pairs. That shape is going to be that trigonal planar shape, 3 atoms surrounding the central atom all in a plane. But if I do have 1 lone pair, then I get bent. So this would be a situation where maybe I have one of these bonds is gone and then I have one lone pair, whereas the core shape, the electron shape, is still trigonal planar because these pieces are all in a plane. I have now what's called a bent shape, where this, if I ignore the lone pairs, this thing is bent. It's just they're not in a row, it's bent. Now we look at the tetrahedral shapes. So if I have 4 electron domains and no lone pairs, that's tetrahedral. This is that methane again, or carbon tetrahydride. Has 4 electron domains, no lone pairs, that shape is going to be a tetrahedral. We've seen this time and time again. Let's clean this up and make these all single bonds. Boom, boom, boom. So now I have that tetrahedral shape. I have the electron geometry being tetrahedral as well as the molecular geometry. Now, what if I have one lone pair? Let's do this. I'm going to turn this off and see what you call it. I'm going to get rid of one of these bonds and do my 4th electron domain, and I'm going to go ahead and add the lone pair. What do we call this shape? Let me tilt that up a little bit. What do we call this shape? Let's not show the lone pairs. Okay, see how we have something that looks kind of like a pyramid? A really shallow pyramid, but a pyramid where the 3 atoms are all in the same plane as themselves, but they're all below that central atom. That shape is called trigonal pyramidal. It's a pyramid with a triangular shaped base. Here's my, I got 1, 2, 3 atoms make the base of the triangle. The purple one is the apex of the pyramid. So if I have 4 electron domains, but one of them is a non-bonding pair, then I get, wait a second, and then I get a trigonal pyramidal shape. This is what happens with ammonia. We saw this earlier with the weird little shape. Now, what if I go ahead and remove one of those bonds and I add another non-bonding pair or lone pair? What's that shape? It's bent. It's just a different bent. This one's bent a little more than the other one. The other one was bent only to 120 degrees. This one's bent to 109.5 degrees. That's bent. So when we have 4 electron domains and 2 lone pairs, that's going to be bent. We wouldn't have 4 electron domains and 3 lone pairs, but if we did, that would be linear. So let's do it. We can do it with the simulation. Throw another one there. Look at that. Look at that shape. Tetrahedral. Here's the top piece here. Tetrahedral shape. But get rid of those lone pairs. Don't show them. All you have is a linear molecule. So here's an example of acetic acid. Acetic acid is a compound, and we have 3 different electron domain situations. This one on this side has 1, 2, 3, 4 atoms around it. So it is going to be a tetrahedral shape, and they're all bonds. So around this one on the left, its geometry is tetrahedral. On this one in the middle, I have 1, 2, 3 electron domains. And I will tell you on this central atom, there are no lone pairs. So in this situation, I would have this shape around this central atom, the one in the middle, as being trigonal planar. And this one, this corner here, unfortunately, this corner here doesn't show it well, but this red atom here, which is a oxygen, has 2 more sets of non-bonded pairs. So this shape would be just simply bent. So it's tetrahedral around this atom, trigonal planar around this atom, and ultimately bent around this atom. So that's where we're going to stop with the molecular geometry. I think you just need to get a little bit of practice. The PhET really, really helps out because it gives you a chance to play around with the shapes and see them and manipulate them in real time. I will be back with lesson 5, the last part, where we talk about polarity. Toodles.